in terms of your vision for how we can realize AGI, you talked about combining neural networks with other kinds of approaches like neuro-symbolic systems, evolutionary learning, knowledge graphs. Could you dig into those three approaches and uh, and describe how they can
Yeah,
enhance?
absolutely. So yeah, I think as most of the people listening to this podcast probably realize, the AI field has been around since the middle of the last century. I mean, the name was invented in, I guess, the late 50s, but goes back a couple decades before that. Probably Norbert Wiener's book on cybernetics was the first place that really laid out sort of AI as a discipline for making machines do the kind of thinking that brains can do. That would have been in the mid 40s sometime. Like, I'm old, but not that old. I was born in the late 60s, right? And during that long history of AI field, a lot of different AI approaches have been put out there. I mean, neural nets have been there since the 40s, but logic systems have been there since 1960s, I would suppose, and evolutionary learning that tries to emulate the process of natural selection to do thinking. This has been there since the early to mid 70s. Host of different AI approaches have been around for a while and deployed in commercial systems across various vertical markets with sometimes great success, sometimes less so. Right now, one of the interesting things we see with the whole LLM revolution is just taking stuff that's not that different than what was done before. I mean, decades ago, even with some minor tweaks, deploying it at way larger scale makes some quasi magic happen, right? And it's pretty cool. I mean, I remember in the late 90s, mid 90s, I was teaching cognitive science in university before I bailed on academia to go into industry. I was teaching neural networks with a neural net with like 35 neurons trained using recurrent backpropagation on a decent like Sun Unix workstation. Take 3 or 4 hours to train that network with 35 neurons, right? And I would tell the students, well, okay, this is 35 neurons. Your brain has like 100 billion neurons, but it's got massively parallel infrastructure. Like as hardware gets better and better, we're going to be able to train these software networks, similar to how the brain does things. At the time, I was working on a connection machine from Thinking Machines Incorporated, which had like 128,000 processors, like MIMD parallel, 128,000 autonomous processors doing different things. That could train a neural net much faster, right? They've stopped making
Yeah.
that kind of hardware. We got GPUs instead. But in the end, what I told those students is basically accurate, right? I mean, now we can train a load of neurons in a neural net. It's fast and it does amazing stuff, which is just what I thought would happen. Honestly, I thought that was going to take 5 or 10 years, not as many years as it has since the mid 90s. And there's been architectural changes, right? So transformer neural net, if you go back to the attention is all you need paper, a lot of what happened there is you took recurrent neural nets, you stripped out some of the recurrence and replaced it with an attention mechanism. Now that decreases the computational capability of the network. I mean, in terms of just theoretical computer science, a vanilla transformer neural net doesn't compute all the kinds of things. It can't bisimulate all the kinds of automata that a recurrent neural net can. I mean, if you give it an external memory and a scratch pad, it can kind of do it, but it not natively, right? So you're weakening the computational power of recurrent neural nets by replacing recurrent layers with attention, but you're making it easier to train at a huge scale, right? And that's really interesting. We don't yet know exactly how much of the loss that you get from getting rid of recurrence can be gotten back by other tricks within the scope of transformers. But it's clear like we can do so much amazing stuff by sort of scaling up a fancy version of the multi-layer perceptrons they were working with in the late in the late 60s, right? So now you go to other AI paradigms like logical theorem proving, right? Well, in some domains, we already see what can be done by scaling them up in modern computing infrastructure. So, my oldest son, Zarathustra, just submitted his PhD thesis in the Technical University of Prague on using machine learning to guide automated theorem proving. So, I mean, if you take a corpus like Mizar, which is a list of huge number of mathematical theorems going to the PhD level and beyond, pretty rapidly, a machine learning guided theorem prover can prove like 80% of them, just zing, 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 right? So, I mean, certainly more than I can do in a few hours' time. And my PhD was in math, right? Now, they're not good at making up amazing new math theorems, which is what mathematicians have fun doing, but they can prove things very quickly and very well. And again, the core concepts behind today's automated theorem provers, they're not that different than the core concepts behind automated theorem provers from 20 years ago. It's just, we've optimized the code behind these, but we also have just much faster computers to run them on. And having the internet where you can make a corpus of all math theorems and just try stuff over and over again on this corpus, tune the parameters of your theorem prover and the machine learning that guides it. I mean, this has allowed conceptually similar ideas to the ones from decades ago to be refined in such a way they're super, super good at theorem proving, right? And I think the same holds in a bunch of different areas. So we could look evolutionary learning. The idea there is you're simulating the process of evolution by natural selection, like mutation and recombination and selection of the fittest entities. So the basic dynamics of evolution of populations of biological organisms you're simulating inside a computer. One example of evolutionary algorithms, stopping short of AGI, which I'll talk about in a moment, but just to understand the impact of the modern ecosystem on making evolutionary algorithms work better than they used to. I mean, in the mid 90s, I used genetic algorithms, floating point genetic algorithms, to evolve the coefficients of iterated function system fractal generators to generate sequences of melodies, musical notes. And I then used a rule-based AI system to modulate the timing, and I was able to generate some quite cool music. I mean, either modern classical, or I made it generate like long rhythm guitar and lead guitar stuff that sounded like, epic versions of the middle of Master of Puppets by Metallica or something. Right? It was cool, but I mean, I couldn't get the timing to be interesting from the evolutionary algorithms. So I made a rule-based system based on some music theory to do the timing rules. And I mean, the timbre I just did in a standard computer music way. I used the GA just to evolve the practical coefficients, generate a series of notes, like a MIDI file for those who do computer music. So that was interesting. And the mutation and crossover of a genetic algorithm, it lent some creativity to the proceedings, right? So instead of, at the time, what people were doing in AI for music was like Markov modeling, like you just generate a probabilistic model of this series of notes and generate new series of notes by instance generation from that distribution. And I mean, that's cool, but it gives you something that sounds like a second-rate version of the stuff in the training corpus, right? And genetic algorithms generated a bunch of garbage, but they also generated stuff that was new sometimes. So now I've been revisiting this area, but in a modern way, right? So you can take something like Music Gen, which Facebook has conveniently released recently into the open source, which is great. Unlike Google, that did not release their Music LM into the open source. So good for you, Facebook. Bad for you, Google, in this particular case, right? And so Music LM, you can give a text prompt and optionally an audio file, a music file, and it generates new music conditioned on the music file, guided by the text prompt, right? And It's very nice. It generates stuff that sounds like music. Now, what I found is just using its prompts, it generates music, but it's sort of cliche music that doesn't interest me musically, even though it's very competent. If I use my own weird music as the melody prompt, then it generates stuff that I find interesting, guided by the text prompt. Now, since it's open source, if you plunge in and see how they use the melody prompt, it's very crude and simplistic. So I'm currently mucking around in there, working on some better ways to do the conditioning on the melody prompt. If I get anything awesome, we'll release that open source also.
Nice.
But what
Looking
I'm
forward to
playing
it.
with genetic algorithms is use a GA to evolve prompts, right? So using a genetic algorithm to do mutation and crossover, and then probabilistic instance generation on prompt space. So you have a genetic algorithm, you're mutating prompts, you're taking a prompt and combining it with another prompt. Then as a human, you listen to the music that came out from a given prompt, you rate it for how much you like it, and then you feed your evaluation back in as a fitness evaluation to the genetic algorithm for prompt evolution. Then you can code rating functions which embody like a mathematical model of musical aesthetics, and you use that for fitness estimation. So if your rating function says this sucks, you don't listen to it. If your rating function says it's good, then you listen to it and give it a rating as a human to feed back into the as a fitness function of the genetic algorithm. So the thing is, using this spiritually, it's like similar to what I was doing in the 90s, right? Using a GA to try to evolve some parameters that guide another process that generates music. You can listen to it and rate it and try to get something creative. But now it sounds like great diversity of music in any genre with any number of instruments, right? And that's super interesting. I mean, this is because you have a model like Music LM, which is bottoms out on all sorts of like sequential models of music, and LLMs doing the text to music mapping and so forth. So we've got a lot of underlying technology that lets the same concept of evolutionary learning of the coefficients of a music generation process work now just much more flexibly than in the 90s. And now like all the parts are done within the same AI process. Whereas in the 90s, it was like, okay, use your GA and fractal generate melody, then find some other music theory way to generate timing, find some other way to generate timbre. Like now it's all in the same AI process. So what we've seen in many domains here is more data, more compute, same conceptual ideas, lets you tweak the specific algorithms to a way that makes things magic and makes things super cool. Now, what I think is, this is going to let us actually make artificial general intelligence at the human level not too long from now. Let's say 3 to 7 years from now. And I think once you get to artificial general intelligence at the human level, if it's done in a non-stupid way, that's going to relatively rapidly lead to artificial intelligence at the way beyond human level.
Yeah,
Because
artificial super
AGI at the
intelligence.
human level, yeah, I mean, if the AGI is as smart as you or me and has full read and write access to its source code, I mean, it's going to figure out how to revise its source code, and it's going to uplift itself to artificial super intelligence, which leads to a whole class of issues that we can get to if we have time. But let me come back to logic systems and evolutionary AI and knowledge graphs, and how I think they can potentially be used together to make the leap from really cool narrow AI systems like ChatGPT and like the other things I've been doing to artificial general intelligence. So first of all, I'd say nobody solidly knows how to make the leap from where we are now to human level artificial general intelligence. I mean, it's a research question. Last week in Stockholm, we had the 4-day long AGI 23 conference, which is an artificial general intelligence research conference. And I've organized that conference every year since like 2006. This was obviously more LLM heavy than most, but you had a bunch of other sorts of AGI ideas and a bunch of hybrid LLM logic and other sort of system talks. But there's a broad spectrum of ideas about how to make the leap from here to AGI, and I'd encourage people to look at on YouTube the video proceedings of that conference. I mean, the first day we had a workshop on OpenCog Hyperon, which is my own primary AGI attempt now, but the main body of the conference had talks by all sorts of other people. I mean, if you're interested in large language models, if you look at Noah Goodman's talk showing how good large language models are doing elementary math, and then Selmer Bringsjord's talk discussing how terrible large language models are at doing slightly more advanced math and logical reasoning. It's an interesting sort of counterpoint.
Yeah.
So one approach to making AGI will be to, try to make it GPT-7 or something, right? I mean, take a large language model, plug more stuff into it, right? Plug Wolfram Alpha into it for calculation thinking, right? I mean, plug some sort of long-term memory into it and some sort of better working memory into it, so it keeps a thread during a whole conversation and has some coherent lifelong experience, right? Plug the best video processing models you have in it so that it can intersect video and language fluently, which is almost but not quite there, right? So for music, like right now, GPT-4 has never listened to music. No one knows the text associated to music, but I mean, you could make it intersect it, co-train it with a different neural net that's seeing it inside music. So that would be one approach. Now I'm working centrally on a different approach, which is within a code base called OpenCog Hyperon, which is a new version of the OpenCog open source
Yes.
AGI
This was my very next
platform. But
question
I
for
mean,
you. It's perfect.
yeah, I mean, the core idea there is you take this large, distributed, potentially decentralized knowledge graph, or more properly, it's a metagraph, not a graph, but same concept. I mean, it means like a graph in a sense is nodes with links between them. A hypergraph is like a graph. We can have one link spanning 5 nodes or 20 nodes or something rather than links being binary. A metagraph is even more general. It could have a link pointing to links or a link pointing to a whole subgraph. So we take this knowledge metagraph and we use it as a sort of knowledge meta representation where you can put all sorts of knowledge in the same metagraph. And that includes logical knowledge, it includes neural net distributed knowledge. It can include programs. So you can embed a program inside this knowledge metagraph. And of course, inside a C++ compiler or a Haskell compiler, you have a graph representation of a programming language, of a program, right? So, I mean, representing programs as graphs is nothing new. But here, it's the same graph used to represent declarative facts and beliefs, neural networks, or which are themselves nodes and links, right? Or
Yeah.
programs. And then pieces of that graph can then be sort of brought alive by different software processes. So if you have a program stored in the graph, an interpreter can grab that program and run it. And then the program stored in the graph, what do they do? Well, they transform the graph. They pull knowledge out of the graph and they rewrite the graph, right? So we made a special programming language called Meta Type Talk, METTA, which basically is a programming language encoded in the graph. And what it encodes is graph transformations, right? So then basically you have this big distributed, decentralized, self-modifying meta-knowledge graph, right? And that's a framework. You could use that framework for a lot of different things. And what we're using it for now is doing probabilistic programming. We're using it to do probabilistic and fuzzy logical reasoning. We're using it to do evolution of programs that are stored as subgraphs. And we're interfacing this knowledge graph with external software libraries running deep neural networks. So you can run a deep neural network totally inside the Hyperon metagraph. It's just not as fast as running it in Torch or TensorFlow or something. So what we're pretty much doing is we have nodes in our knowledge graph that have references within the Torch compute graph. But then you actually do the neural net stuff in Torch at this moment, just because it's faster. I mean, it may not always be faster, but
Right.
it is right now. So what you have here, you have the ability to do, deep vision model or large language model stuff outside of the Hyperon system. You then have the Hyperon system that can drive and interact with and guide these neural systems. And you can then do logical reasoning in the Hyperon system and evolutionary learning in the Hyperon system. And all this is designed to be rolled out on the SingularityNET decentralized AI platform and leverage NewNet for compute resources, leverage the Zarka decentralized LLM for language modeling, leverage True AGI's infrastructure for rolling out APIs based on all this, and hypercycle ledgerless blockchain, blah blah blah. Like, it's designed to leverage this whole decentralized tech stack that we've built in the same way that OpenAI is integrating this stuff with the whole Azure centralized tech stack, right? So what we're planning on doing with this over the next couple of years, I mean, in the big picture, it's everything, right? Just because AI will eat everything, but there's a few critical development directions we're looking at. I mean, the most commercial one is just trying to make something that's twice as smart as ChatGPT by kind of deeply integrating a probabilistic logical reasoning engine with an open source LLM. And we're building our own open source LLMs, but you could also do that with Llama or whatever other open source LLM you want to work
Mm-hmm.
with. So the core idea there is make something that's smarter at multi-stage logical reasoning that integrates linguistic with quantitative and relational data, and make something that's more creative and sort of less banal in its creative productions by adding on a logic engine and an evolutionary learning engine to an LLM in a framework that was designed for interaction of AI from multiple paradigms, right? So that's one thing. I mean, if we can pull that off on a decentralized infrastructure, then we're doing very well in a number of dimensions, right? Now, another thing we're looking at, which is more on the research side, is controlling a bunch of little learning agents or like baby AGIs, and not like the bogus thing that stole my term baby AGI for a chat GPT wrapper, right? But I mean, making things that really are like young artificial general intelligence, like AGI toddlers trying to learn about the world. So I want to make a
Mm-hmm.
bunch of little guys in a virtual world, and we have our own virtual world we're building called Sophiaverse, which will have a bunch of avatars that look like the Sophia robot rambling around. But I also want to have these little AGI toddlers rambling around in Sophiaverse and just interacting, building stuff together, chatting with each other, learning as they go. And that I would like to also do this within little like small toddler AGI robots. I'm not sure if we'll pull that off, but we'll definitely do it in the virtual world. And that, I mean, these may not be as smart in terms of passing exams and stuff as a chat GPT initially, but the idea is they're learning from the ground up from experience. So I think both of these are interesting. I mean, chat GPT has set the bar reasonably high in terms of practical functionality. So we want to surmount
Right.
that bar by just plugging LLMs into our system. And I mean, we can now use LLMs themselves to translate natural language into higher order predicate logic. So we can feed our logical knowledge base with all the knowledge on the web and feed that into reasoning engines, right? So that's cool. On the other hand, I think there's a certain element of creativity and an element of like being an autonomous agent and charting your own path for the world, of understanding who you are and understanding who others are and what's the relation between yourself and others. There's a lot of cognitive things there that people do, which may be easier for an AI system to learn if it doesn't have like half versions of all the knowledge of the web in its mind already. It may be easier for an AI to learn if it's really just making sense of itself and the world in a simpler setting, like a young toddler does, right? So I think we can do both of those things with OpenCog Hyperon in parallel. One is more commercial, one is more pure research. I mean, we're also doing other stuff. The first thing we loaded into our OpenCog Hyperon distributed app space is a bunch of bioontologies. Actually, we've imported all knowledge about fruit fly genomics and a lot of ontologies of human genomics. And we're just because I have some colleagues in the Rejuve biotech project where they have all this DNA data from fruit flies that live 5 or 8 times as long as normal fruit flies that were evolved over 40 years to live a long time. And
Wow.
they actually need an AI system like this to understand why the flies live so long, what that might mean for human genomics, right? So they're using it hands on. So I mean, it really spreads out in every direction once you manage to integrate these different things together.
Mm-hmm.